See, we will again start the static aeroelasticity from the basics. Very simple problem. We will consider the divergence of a 2D section, and we will consider an aerofoil whose the torsional stiffness of the wing is idealized as a torsional spring with the spring constant k theta, and this spring is at the location which is the elastic axis. Okay, I will write elastic of the wing, because this is a 2D model, and then we have the aerodynamic center we call it, this is EA, this is AC, and the wing chord, take it as C, but it is a, and then the offset between the aerodynamic center and the elastic axis. Aerodynamic center, elastic axis, that you call it as E, and if the aerodynamic center is ahead of elastic axis, E is positive. So that is a notation. And then we will take this is at a angle of attack, which is the oncoming flow is U. The angle of attack, we call it alpha effective, is some alpha rigid plus theta. What I mean by alpha rigid plus theta is, alpha rigid is the initial angle of attack which you have set the 2D section, but due to flow, due to elastic deformation, the angle of attack has changed through an angle theta. So the net angle of attack is alpha r plus theta. Now what you do is you write down the equilibrium in torsion. So for that, your aerodynamic load acting on the airfoil is a 25% chord. You take, this is my lift, and take the moment like this. This is MAC. So I am taking counterclockwise movement last. Okay. Now you will have your aerodynamic moment. I will call it aerodynamic moment above elastic axis, about EA. This is okay. Now the expression for lift in subsonic, we will take it as all subsonic incompressible flow. So we can write it as, this is dynamic pressure into area which I take C into some depth. Okay. Instead you can always call it as C into the depth as the area. Okay. And then CL alpha. C lift coefficient, but we will write the lift coefficient as CL alpha times angle of attack, which is the effective angle of attack, which is alpha r plus theta into E. This is the lift and this is the offset distance, plus aerodynamic moment, you will have Q, again area, and one more C will come because of the units, and then you will have a Cm0. Okay, and the very fact that you define aerodynamic moment is it is independent of the lift force. Okay, that means it is independent of the angle of attack. Now this moment is counterclockwise, acting about this point. Now what you do is you have to, because of this moment, the spring is deforming. The spring will give a counter moment. Okay, the spring moment will be, or you can say the, okay, spring moment. This is essentially, or you can call it elastic moment. This is aerodynamic moment, this is elastic moment. This is nothing but k theta into theta. This is the spring moment. That means since it is equilibrium, they must be equal, because as per the diagram, lift and moment will give you clockwise moment. This will give you counterclockwise moment. So when you add them, actually you put a minus sign, or in other words, you say that net satisfying the torsional equilibrium. That is the key, because you are saying that my wing is in equilibrium, static equilibrium. You equate both of them. When you equate both of them, you will have Qs Cl alpha into alpha r plus theta into E plus SC Cm naught equals k theta theta. Okay. Now what you do is you take the theta term to the right hand side and write it like this. You will have k theta minus q s Cl alpha E into theta equals, you will have q s Cl alpha alpha r into your E plus q s c Cm naught. Okay. Now basically I want to solve for what is the elastic deformation. Now if I solve this, I will get my elastic deformation as this expression. Here is this. So you will get theta equals q s Cl alpha alpha r into E plus q s c Cm naught over k theta minus q s Cl alpha into E. Okay. Now we have to just analyze only this. Okay. When you look at it, what are the variables and what are constant? Okay. The only variable is the Q, which is your dynamic pressure, which you define at half rho U square. Okay. Whereas all the other quantities are fixed, because your area, the characteristic of the aerofoil, and your rigid angle of attack, this offset, Cm naught, everything is fixed, E is fixed. Now, as you increase your Q, then what will happen? This term is positive. So, as you increase your Q, slowly this term is increasing. And then at one point, it can become equal to that. When that becomes equal, your theta is infinity, which means the condition theta is infinity means my wing is completely twisted. Okay. Now the condition when k theta equals q s cl alpha into E, or in other words, you write this is the QD. QD is the divergent dynamic pressure at which these two are equal. So you will have k theta over S Cl alpha into E, or you can write UD square is half rho. So you will get 2 k theta over rho S Cl alpha. This is my divergent speed. This is the divergent speed. You can take the under root. If you want, you can define UD, put it under root. This is my divergence speed. Okay. Now you see the divergent speed is a function of course, the torsional stiffness, density of air, yes, as you go out higher, and the area, this is Cl alpha. The key is another, the offset between elastic axis and aerodynamic. Aerodynamic center, subsonic if you say, it is a quarter chord. Now, elastic axis is a, okay. Now the question is, you have to place the elastic axis properly in your aerofoil design. Given the aerofoil section, how do you design my structure such that the elastic axis comes close, because the E is small, what will happen? That divergence speed increases. But if E is negative, that means elastic axis is ahead of the aerodynamic center, then divergence speed is imaginary. That means there is no wing cannot diverge. Okay, there is no divergence speed. But in normal wing design, it is not possible to put the elastic axis ahead of the aerodynamic center. Okay, it's usually you will find that this may be somewhere around 40%. Elastic axis will be around 40% of the wing. But in the case of a rotor blade, it is structurally designed to bring this here, right at 25% chord. Okay, in the rotor blade design. So there you have to do a lot of iterations to see where I put the structural property, because this is an aerofoil. I want to shift this to here. Okay. Now this is where you should have studied the aircraft structures one. How do I identify the location of the elastic axis? Number one. Number two is by doing what structural modifications I can shift them. And these are all thin walled structure. You can have 2-cell, 3-cell box beam. Okay, you have to know that. All right, now you know the divergence speed. What we have done is essentially we assume first, because there is an elastic deformation and that angle of attack has changed. Okay. Therefore, my lift force is changing. On the other hand, usually what people will do is, if I don't consider the elastic deformation in the estimation of my air loads, that is like a rigid airfoil. If I don't consider, then what will happen? My alpha, this is like in a wind tunnel test. Wind tunnel test, what do? You put it at different angles of attack of a rigid model and measure the lift, the moment, etc. Drag. Here we are neglecting the drag force, basically. So, at that condition, the moment equation, that is what we are doing is, we are neglecting the elastic deformation in the estimation of air loads. If we neglect that, our moment equation will be k theta theta equals basically your q s CL alpha alpha r into E plus you will have q s c c m, right. That means I say that this is with an assumption that my airfoil is rigid. So, I try to put a symbol R just for differentiating between that theta and this theta. Okay. Now, if I calculate what is the error between the theta which is defined there and the theta which I am writing it here. Here this theta r will become just simply divided by k theta, right. This, if I calculate theta, form an expression, okay, this is going to be what? What will be the expression? You just write that, okay. That will be k theta, I am just writing, theta over theta r will become over q s E, which I can write it as q is any dynamic pressure, but I have defined my qd as k theta over s CL alpha E. So, I am going to replace, I divide by k theta everywhere. So, it will be 1 over 1 minus qd, or in other words it is 1 over 1 minus u over u divergent square, okay. I erase this drawing. Now, you have a relation like this, theta which is evaluated taking into consideration the elastic deformation in the aerodynamic loads. Theta r is, I do not care, I just say this is my angle of attack. Initially I said this is the moment, and then I get it as though it is rigid. If I plot this as a function of u over ud, that means dynamic pressure with as a ratio with respect to the divergence, okay. So, I will have, if I draw this diagram, because this is a very interesting diagram, just to see why take because u over ud maximum 1, because after that the at 1 is wing has failed. And here you take when u over u is actually, u is very small, when it is 0, you will find that this is, you start with 1, maybe 2, maybe 3, etc., etc., you go. Okay. Now, if you plot this curve, it will be like this. Here I take it as 0.5. 0.5, this is 1.0. That means when this velocity is very small, I have to get the diagram something like this. Okay. And then it will go okay, maybe what you will find is, even when u over ud, please understand, if it is half of the divergence speed, then this is 0.5. 0.5 square is 0.25. 1 minus 0.25 is 0.75. That is 4 over 3 over 4, it will become 4 over 3. 1.33 times you will have the rigidity. That means about 33% more than what you predict with this approximation. Whereas if it becomes, this is 50%. If it is 60, 70, as you go higher, you will find that this is going to become very large. That means the error you make is going to be very large. Why it is necessary that you need to take this? It is not to calculate your divergence speed, because structurally you are twisting it more than what you predict by this assumption, which means the stresses which you calculate using this assumption will not be correct. You need to do a aeroelastic analysis to really predict what is the correct value of the stress. Then only you can design your structure. Okay. That is why in the aircraft structural analysis, initially in the preliminary design, you will not be bothered about elastic deformation and other things. You will make your design. But after that, you have to do an aeroelastic calculation to see whether the stresses are within the limit. Otherwise, you are predicting even half the divergence speed. You have about 30% increase in your twist. That is at the half. If it goes more, then you may be 2, 3, 4 times, it may keep on going up. Then as a result, you find that this is very essential for you to take into account aeroelastic deformation, or you can say aeroelasticity as a topic is very important in the design of your aerospace structure, because that is the key. Otherwise, you don't have to bother about that. That's why we say the wing is flexible. It is only when the structure is flexible, the study of aeroelasticity plays a very dominant role. Now today in the design, they call it multidisciplinary optimization, in which the aeroelastic constraints are brought in right at the design phase, preliminary design phase itself. Then only your structure can be optimally designed. Okay. So this is as far as the simple divergence is concerned. Next we do the aileron reversal. Again, very simple approach. Once you understand that what we mean by the divergence and aileron reversal or control effectiveness, then you can proceed further with your actual 3D. We will take a wing. This is only a 2D model. Okay. Next we take the aileron reversal using a similar 2D model only. Okay. Is it clear? Because I want you to understand that this is a very simple problem. I keep this part here because I may need it. We will take aileron reversal. Okay. As usual, we take a 2D airfoil, but with a control surface okay, and here you have the oncoming velocity u, alpha effective is alpha r plus theta, and your lift is norm okay, aerodynamic center, you have a lift and you have a MAC. Okay. And this distance is, as usual, we have the E, and this is my, you can take it, this is my card. Okay. Please understand, initially beta is 0. Okay. Now this is the control surface. You say that the airfoil is kept at a angle of attack alpha r and with a velocity u, okay, and u is small, you can take it small, okay, but small in the sense small what? It is not a divergent speed, okay, please understand, it is flying at a speed much lower than u divergence, that is essential. Now what do you do with the control surface? Control surface, essentially you operate to change your lift. If you are flying at the same speed, if you want to turn, what you do? You deploy your aileron and you change your aerodynamic lift. So please understand, in this case it is only the change you are looking at, not the actual lift. That is the essential. You are looking at the change due to beta. Okay. So I am going to write my delta CL. Okay. That means, please understand, this is the change in my lift coefficient. I am putting it delta CL, change in my lift coefficient. If you multiply by dynamic pressure, area, etc., you will get the change in lift itself. This is, I am writing it as delta CL over delta beta beta. That is number 1. But because of the change in lift, there is a change in the theta also, because theta means the angle of attack. Because of the change, there is a twist. So I am going to write it this as plus into theta. Okay, and then you will have your change in moment also. Delta Cm, this is, you will have delta Cm AC over delta beta into beta only. I don't put a theta because my moment about the aerodynamic center is basically independent of the angle of attack. Okay, that is why I don't put theta here. Please understand. Beta is change in camber. Theta is change in angle of attack. Okay. Now you know that this is delta CL over delta beta is change in lift due to unit deflection in. This is change in lift due to unit change in the angle of attack. This is CL alpha basically, and this is change in moment due to a unit deflection in beta. Now what happens is again you have to balance because this is in static equilibrium. So you have to balance the change in moments. Now it is not actual moment, it is a change in moment. Okay, aerodynamic moment is basically, you can call it aerodynamic star Q dynamic pressure into your lift coefficient. That will be basically delta CL over delta beta times beta plus delta CL over delta theta into offset plus card delta CM AC over delta beta times beta. This is the aerodynamic moment, and your elastic moment as usual this is going to be T elastic is K theta into theta only. Okay, and these two are equal for equilibrium, T elastic. Now you equate both and then you collect the terms of theta on one side and leave the beta terms on the other side. If you do that, what will happen is, I will write that expression, you will get directly, I am putting it, okay, theta over beta equals E delta CL over delta beta plus C delta CMAC over delta beta divided by K theta over QS minus E delta CL over delta R. Okay, this is the you check it. Okay, what we have done is we have just taken the change in lift and the change in moment due to in the control surface, and then equilibrium, static equilibrium. Aerodynamic moment we calculated about the elastic axis. Please understand, this is about elastic axis, and this is anyway K theta into theta. You equate both of them and you got now a relation between the angle of attack change, please understand, to a deflection of the control surface. So if I know the control surface deflection, I know what is my angle of attack change, theta. That means I can always, I have an expression now, theta in terms of beta. Delta CL is my change in lift. due to a deflection in beta. Now I can go and substitute theta in terms of beta in this expression. Okay. If I do that, I will have change in lift coefficient due to a deflection in only beta. So if I do that, I can erase this part and write the. So please understand, I am substituting for theta in terms of beta in this expression, and I will get like this equals delta CL over delta beta, that is this term, plus you will have into the entire expression E delta CL over delta beta plus C CMAC over delta divided by QS wait 1 minute, is it QS into, there is one okay, QS only, QS into minus E delta CL over delta, and this entire expression is multiplied to beta. That means now I have an expression which says if I have a deflection in the control surface beta, what is my change in lift? And what I have to do essentially is, here I have to do some rearrangement jugglery. It is basically some algebra. Okay. Algebra, I erase this part because now this is what is the key thing which you have to analyze. You put them as a numerator and denominator, etc. Okay. Simplify this expression. I erase this part. You will have your delta CL becomes, I am simplifying this, please understand, this is delta CL over delta beta K theta over, because you can simplify this, E Q S delta CL over delta theta. Okay. Delta theta or alpha? What is that? This is alpha I am using. Am I using alpha or theta? Huh? Theta, no, I think let me put it theta only. So don't change it to, I am sorry about the change in symbol. Okay. And then I will have what? Plus C over E delta CMAC over delta beta divided by K theta over E Q S delta CL over delta theta. Okay, please understand, I have essentially taken, because you see delta CL over delta beta, if I take this term here into E, that will cancel out with this, okay, leaving behind only delta CL by delta theta, this term, okay, and that delta CL by delta theta I will actually eliminate here. In the denominator I have taken this term. That is why that will come out and then put it in the denominator. I am doing it. So this is just an algebra you have to do. Okay. Simplification, I would request that you do it yourself. Now, what we look at it is, suppose the numerator is 0, then what happens? If the numerator is 0, whatever I change beta, it is not going to change my lift CL. But is it possible? That is the first question you will ask. You know that delta CL by delta beta, yes it is, but moment coefficient is a negative quantity. Okay. This is positive, K theta is your stiffness, this is positive, E is positive, Q is positive, S is positive, this is positive. This quantity is negative quantity. Okay. The aerofoil. Now, as you keep increasing your Q, what happens? This term keeps decreasing. At one point, you can make this equal to 0, and that is the control reversal speed. In other words, you say no matter at that speed, whatever I do to beta, nothing is going to change my delta CL is 0. You may have a lift, please understand, that is why lift is not 0. The change in lift is 0. So, that particular condition, now we can, there is this, I will keep this term as it is. Let me write here. Okay. So, you will get delta CL over delta beta into K theta over E Q S delta CL over delta theta plus C over E delta CMAC over delta beta equals 0. Okay. If you take Q, this is condition when Q reversal, I am putting it. But other Q you can have some value. Now I simplify, that is take it to the right hand side and get only QR. So I will write the QR expression. Q reversal is minus delta CL over delta beta into K theta over, because what I have done is I took it that side, I multiplied by Q and divided that here, that is all. Okay. Delta CL over delta theta C S delta CMAC over delta theta. This is my QR. And please understand, E cancels out. So the interesting thing which comes out of this is the offset has no meaning. In the sense, it doesn't matter. Your control reversal speed or aileron reversal speed is independent of the offset between the elastic axis and the aerodynamic center. Right here, that is why I wanted to put it in one place. I can write QR, okay, as minus delta beta over delta CL over delta theta. Theta is basically CL alpha. System is CL alpha. CS Cm is over delta. And similarly, you can define your UR. This will be square root of minus I am again simplifying this delta theta delta CMAC over beta into you will have C S and I have to have rho over 2 K theta. Okay. C S rho 2 K theta. So this is my control reversal or aileron reversal speed. Okay. So you have now speeds which you have defined, control reversal speed. Now suppose again this is an interesting algebra. Okay, I would put it more on algebra rather than much of a thing. It is essentially if again if I say that my airfoil is rigid, then what will I say? Like in a wind tunnel, if you make the entire unit out of wood and then only change the controls, the angle is not going to change. Only thing is your lift will change with respect to beta only. The second effect of the twist that happens. So you will be writing it like this. If I say it is rigid, you will write it only like this into beta. Okay. You will not use any other, because of the change in lift, there is a change in angle of attack, and that change in angle of attack has also changed in my lift. So you see, this is with respect to an actual wing where there is a deformation, torsional deformation, whereas this is on a wing where I don't consider the torsional deformation. Now if I take the ratio of delta CL over delta CR, and you can again plot some nice curves. But that particular simplification, I will write the simplified expression. It is like an exercise which you do it yourself to come up with that expression. I am not going to do the algebra part. Okay? Please understand, this part you do it yourself. But you have all these expressions, so you must use it properly. Okay? I am writing it as delta CL over delta CLR is, it's in a very compact form, 1 minus U over U divergent square 1 over 1 minus U over U divergent whole square 1 minus U reversal over U divergent whole square over U reversal over U divergent whole square. Okay? Please understand what I have done. I have this expression delta CL and I have delta CLR. Okay. What I have done is I took the ratio and then I have formulated this. This is a very neat expression, but this requires some algebra. That I have that with me, okay, but I would like to give it to you as a exercise. One more homework, you take it, try to get this expression from there. Now let us analyze this particular diagram, sorry, not diagram, this particular expression which we have given here. Maybe I erase this part. Okay, so I would request you to try this out completely. If we take a plot, because you see here u is any speed, u divergent is given there, u reversal is given there. Okay. Now I am going to make a plot of the curve which is okay, like this is delta CL over delta CLR. Okay, this is u over u divergent. This is 1.0 minus 1.0, maybe minus 2.0, etc. You can have 0.2, 0.4, 0.8, okay, 1.0, okay. Now you see when u reversal speed is equal to u divergent speed, then what will happen? This is 1. That means u r over u d is 1.0. This is 1.0, so that goes off. That means delta CL by delta CLR is fine. It is 1. That means there is no difference between divergence and the controlled reversal. It really doesn't matter, but my delta CL lift will be rigid, or I make a flexible wing approximation. My delta CL over delta CLR is always 1. Okay, provided I keep my reversal speed and divergence speed same. Suppose reversal speed is 0.9 of ur over ud, that will be something like this. I am taking it like this, here 0.9. So I will draw the diagram, okay, it will go like this. This is ud 0.9. You see what I have done. When ur over ud is 0.9, then what will happen when u, because here this is the u over ud, okay, when u over ud becomes 0.9, then automatically this and this, there will be 1, because this will cancel with that, This will cancel with that, leaving behind 1. 1 minus 1 is 0. So I will get 0 here. Okay. In the delta for delta CLR, I will get my reversal speed. That is what here is. Reversal speed is 0.9 of UD. So the curve will come like this. Similarly, if you take 0.7, maybe here, the curve will come like this. This is UR over UD is 0.7. Okay. Now, the key thing you have to consider is, what is my change in lift? Even if, because you don't fly at reversal speed, you don't fly at divergence speed, you will always fly lower than that. But how much of effective control I am getting? Because delta CL over delta CLR, I must get 1. If I get 1, that is very good. But if my reversal speed is less than the divergence speed, I also find even at, if I fly in this zone at a much lower speed than the divergence speed and reversal speed, I am getting a less effectiveness of the aileron because of the wing deformation. So this is this region, you are actually losing your effectiveness. This is what effectiveness is. This is basically the reversal. Okay. And control reversal, control effectiveness. How much? You may say, I want my wing, the aircraft to roll at this rate. That means it may require, if you want to initiate, you want a roll acceleration. You want so much of, you know the inertia of the aircraft, you want so much moment to be generated. So you will say, okay, deflect my wing through some angle. But what will happen is, when you deflect it, because of the deformation of the wing, what you get as the control moment, it will be much less than what you really intended for. That means your effectiveness is reduced. Okay. Now you can see what is the condition. You can have both UD and UR equal. Okay. That is the best. If you can make reversal speed and divergence speed equal for your design, that's very good. I would like to have it, this is the divergence of a, okay, of a slender straight wing. You can take it large aspect ratio wing. So we will now draw a wing. And this is my x-axis, and this is my z-axis, and I can take my y-axis like this. Okay. And I am going to now define couple of points. This is my, please note, elastic axis EA. My y axis is on elastic axis. This is my aerodynamic center line. And there is also a mass center line. Now, this is my, I will say, center of mass line. Okay. And I as usual we define the offset between the elastic axis and the aerodynamic center, that is by E, and this offset we call it D, that is the mass center and the elastic axis. Now essentially this is my slender wing. I am making this assumption that my elastic axis is a straight line. Straight line. This is, it can go, but it can be tapered, no problem. Tapered, everything. But they all fall in a line. I am just taking it for ease of writing them. Now for this, and this is in a wind speed, so the oncoming wind as a velocity u. Okay, and please understand this is a straight wing. Therefore, your lift is acting here, and there is a moment acting. I am putting it in the lift and moment about aerodynamic center. But this gravity is acting down. Okay, and if the wing is now flying in a load factor condition, you can take the load factor as n, which is, if it is a level flying, n is 1. If it is doing a maneuver or some other higher load factor, so you always take this as some load factor times mg. M is mass per unit length. Okay. You are going to write the only torsion equation for this long straight wing. The assumptions you make couple of assumptions. One is this axis is perpendicular to this, y axis is perpendicular to my root section, and it is a straight line. I am taking it like this. Second one is it is an incompressible flow, and the third is I am assuming strip theory. So we will say incompressible, because I am using a simple incompressible flow, and then I apply strip theory. That means every section I am taking it as a two-dimensional section. I am not taking any 3D effects and etc. Okay, and then the structure is straight. There is no sweep back. That is very important. That is why straight wing I have made that assumption. Okay, later we will do what you have to do for swept wing, and there is no other deformation in the plane of, because it can bend due to drag force, it can do that, but we are not taking all those effects into account. Okay, and third is every chord-wise segment. Okay, you take this, and this length you can take it as L. Every chord-wise segment is rigid, in the sense it cannot bend or anything like that. It can only twist. Okay, this is a simple Saint-Venant torsion theory. So you apply Saint-Venant torsion. Okay, and for this you know the equilibrium equation for torsion, which we developed in the first section. That equation becomes dy gj equals minus, I am putting, this is my distributed torque. Okay, please understand, this is my distributed torsional moment. And this is a, please understand, static problem, so there is no inertia, in the sense there is no vibration part. Okay, you don't say inertia is not, but the gravity is having its effect. Okay, now you have to write what is my Ty, distributed torsional moment. You write it as torsional moment about what? Now you say I am writing this is about twisting about the elastic axis. Okay, this is a twist about the elastic axis. Therefore, I should take moment, all the moment about the elastic axis, keeping dE as the offset point. Now, if you write, you will have Q, which is the dynamic pressure, C, because this is per unit length, QC CL into E, plus you will have C square CMAC minus mg into d, because lift is q, this is lift per unit span. Now that is why it is not a s. Okay, this is q c cl alpha times whatever, you can put it alpha r plus theta, you can put it like this. Okay, which is basically, this is my CL, this term is CL, and then your moment is Q C, and you will have one more C, that is why it is C square CM naught or CM AC, I have put it CM aerodynamic center. Okay. And of course, this is the load factor, which will be minus sign, because this is due to the gravity, which will give a nose down. This is a nose up. Now what you have to do is, I have to go substitute this here, and I will now your CL, because you say initially my aircraft wing is kept at the angle of attack alpha r. Please understand, now all these quantities you have to understand, E, this offset E, D, card, all can be functions of y. Okay, they need not be constant throughout, unless it is an assumption, it is a straight plan, so that plan form wing. Whereas here everything can be varying. Suppose if the aerofoil itself is varying, your CL alpha itself is varying. Okay, it need not have the same aerofoil throughout. Okay, but for the, we will write the general equation, but then when we solve, we will simplify the problem and then solve it as a for a uniform beam. Okay, now let us write the equation with the boundary condition, because this is a deformation of a wing d theta over dy equals, we have put it minus, okay, q c into E. My CL is actually CL alpha times alpha r plus theta. Okay, plus you have q is taken out, so c square CMAC, and minus will become plus n mg d But what you see is this theta term is on the right side, you take it to the left side and your equation will become d over dy of Gj d theta over dy plus q c e Cl alpha into theta equals minus q c square cmac plus n mgd. With the boundary condition you will write, because the free end is free, so I will have moment is 0. So I will put d theta over dy, or you can say Gj, at y equal to L is 0. That is the free end. And then at the root it is fixed. It is attached to the fuselage. I am saying that that is fixed. So theta at 0 is 0. This is a fixed end, fixed root. Okay. Now this is my equation. What you have to do is you have to solve this equation. Oh, I am sorry, I have to add, I am sorry, this, what is that? Minus q c e cl alpha alpha r. Please note down. Yeah, add that term. Yeah. I am sorry about that. Okay. So that is my equation. I need to solve the, yes, q c e cl alpha alpha r. Okay. How do we solve? That part we will do in the next class.